Hello, hello, hello. Up the back. Can I be heard with the amplification? Thank you. Alrighty. Wow, you do love me. I thought you all rejected me and you all went and so upsetting. Anyhow, I'm sure this is all, you're all here. It's got nothing to do with the content I'm about to run through. But maybe I'm wrong on that, so let's get started. I've got a lot of slides to get through, and as well as I said yesterday, for people who have gone through, had a look at the sample exam, you'll get maximum benefit from right now. Those who haven't, doesn't matter. It's all going to be up on LMS. Give the exam, the sample exam a go in your own time, under exam conditions, and knowing that you've got a set of solutions or outline solutions available to you. For people who haven't done mechanical design third year with me, people might think, shit, 38 pages. That's a lot of pages. It's actually, it's actually 70 sides of paper. The reason why it's long is that you don't get script books in this subject. You write in the exam and you, I'll go forward a slide, you don't take the exam paper with you, you leave that and then we mark the paper itself. Lots of advantages to this approach. One of them, for your sake, is that you've got an idea, just by how many pages of lined and graphed information I've got, how much, roughly, how much effort's required. The closed book exam, as far as I'm concerned, whatever the system says you're allowed to have in the exam as a calculator, you're allowed to have in my exam. And also, anybody who's concerned that design is very wordy and English isn't your first language, you're allowed to bring in your bilingual dictionaries. I don't know how the people who walk up and down the corridors, the invigilators, I don't know how they flick through those dictionaries or not, but please, they don't have writing in them or you might have a problem. Other than that, please, please, please don't make the mistake of taking the exam with you at the end of the exam period, the 2 hours, because then you do yourself a disservice. You've already been told that previous year's exams are available for you to review. Some hints. Now, just yell out if you've got a question. This is the time to ask questions while everyone's in the room. First hint is that if you've actively participated in all the design projects, you should be able to walk into this exam thinking, yeah, he's not a bastard. He hasn't given me, two for the associated with the difficulty of the exam. You should be comfortable. You might think, oh, shit, lot of work. You might think, well, that's a bit of a twist in the to what I'm used to. But there should be nothing in there that should surprise you. As, surprise in an exam context means, upset, irritated, freak out, anxious. That's not what I want. I want people who've done the work to walk in and think, oh yeah, got it. I'll get through all that. Sketching, I love. Tables, I love. Essays, in the context of this subject, I hate. So don't just write blathers of, I would have answered this question except I didn't do this and you didn't provide that. No marks in that. Better to give me an outline solution of what you would do or what you think you would do. You might get, if you've got the right method, I can promise you will get marks. Bring a ruler, bring a protractor. A lot of words. This is about material selection. Just so everyone knows, there are a set of material selection charts, those black and white charts up the back of your exam, and you're expected to actively use them in a way that me or one of my helpers in the marking phase can see what you've done and where you've done it. There's not much point just putting a couple of lines here and there hoping to get a mark. You know, own your answer. Clear, if it's pencil, nice and soft so we can easily see it, cross-reference to the question, the part of the question, and then we at least can see where you've made the mistake and perhaps partial marks. If you don't do that sort of stuff, well then we've got you're not giving us the opportunity to give you marks. So please do that. If there is a question associated with tolerancing, limits and fits, you do not, of course you don't, it's a closed book so you don't bring the stuff in, there will be information in the exam that you make use of. For example, a table or two. You've got to choose which is the correct table. You've got to put a big red or big circle around the correct cell, and then you use that information for whatever task might follow on. For those who, let's just say you got your teammate to do all that work in DP4, you didn't do it yourself or haven't done it yourself, all of the associated, Australian standards are up on your website. Now that first point, it's not just might be, there is a question where there is an image and that image has been repeated. It's just a cut and paste for me where I'm setting it. But for you, if you're anxious and you make a mistake and you think, oh, I've used pen and I've mucked up this image where I've got to add probably forces, but who knows what else it might be. You muck it up and think, oh, now I've got this problem. There's 2, maybe 3 images that you can choose from. Just put a big scroll through your mistake, start again. That's what it's for. It's not as if there's going to be, answer one question one way and answer another question a different way. Don't, again, this is just advice. Don't freak out about that aspect. By all means, write on the back of an adjacent page. Your exam is single-sided by and large, so just go to the adjacent page and just make a little note. Every page is numbered. Completed page X. All you got to say, and we'll go there. No script books. And this one. Do not request just sort of free and easy, gimme publication of previous solutions from previous exams. As I've joked, for refusal may offend. You've been given enough, and you're going to be given a bit more in a sec, but I will schedule down the bottom in blue for those of you who are keen, who do attempt to solve questions in some of the previous year's exams and would like to know if you got the correct answer or not. There will be I'll schedule a session closer to the exam date where you can get a bit of assurance and certainty about the correctness of your exam. But just as a reminder, it is not a tutorial. It's not just going to be everyone just sits there and answers are going to be put up on the board. We're just about done with that. Everything else on that slide in red has been emailed to you already. This Friday, last minute question and answers for DP4. I've got all my tutors trying to get them all in gear so that it'll be DP4 will be marked by next Thursday, fingers crossed, so that next Friday there will be a handback, Q&A, and then informal, actually a little bit more formal than that, but there will be solution outlines for all the 4 assignments on the whiteboard in D207. Hint, it might be PowerPoint to get through them more quickly, but again, this is not a session where Farouk or Jacob probably will be looking to see whether you've got mobile phones sticking out. And if anybody starts putting their mobile phones out, well, everyone will be disappointed. Same thing is true for this one. I have to tell you this, I'm sorry, this is a negative thing, that as soon as I or whoever's doing that for you, that Q&A for exams, see someone trying to take photos of my solutions, at the end, finished. There's, trust is a very important thing. And this is all about you doing work, not sort of trying to sneak stuff. So I hope that you'll work with me in that way. Another thing to say, though, is that people who have succeeded, if you've got 50 out of 100 for 50 marks out of the total of 100 for this subject, so 50 out of 60 for your assignments, you've already passed. If you've got 40 out of 60, you've got 10 marks to get in the exam and you've passed. More of that in a sec, because someone asked me that by email, and I'll get to it. Ooh, what's he talking about? just wait. Woo! I shouldn't have said it. Perhaps I shouldn't have said that. Hang on. What's he talking about? What's he talking about? You will see graph paper in the exam. You will see formulae in the exam. But you will not see those three formulae. They might be in the exam. They're not there in large part because they're such simple equations. Even that square root of 2 squares is pretty simple for 6 sigma. That will not be in the exam. But I've mentioned it, which sort of implies it might be important for the exam. So now everyone has that bit of information. You will not, it's good to review. This is actually my copy that I scanned of AS1654 for tolerancing. In previous years, students printed off bits they needed and brought it into the exam for open book. Closed book now, your life's going to be a bit easier if there's an equivalent question on your exam. This is an image of something that you will see in the exam. And there's a big hint on that image associated with the object that you will see in the exam. And the reason I'm showing you this object is, a generation ago, this slide, what I'm saying right now, would not be needed because everyone in the room would have come through, mechanic or working in a factory or having a real sort of hands-on appreciation of the nuts and bolts of engineering and mechanism and machines, etc., etc. We can't assume that in this era. That is no one's fault, and it's not even a negative. It's just about, to be blunt, ignorance doesn't mean stupid, but if you're ignorant of what that is and you see it in an exam, that's unfair. Everyone in the room now has the opportunity to go to Wikipedia and learn a bit about that object, or go to Bunnings and learn a bit about that object. Everyone is now aware that you will see this image in your exam. You will also see the same image cut in half on 2 different pages to make sure that when to be blunt, the rather average printing we get at times doesn't turn some of the important numbers that you may need into just gobbledygook. So, now you know that there's going to be some questions similar to questions you've already answered for an assignment. And this one is to indicate that it's going to be zoomed in so you don't have to be nervous that, oh God, am I going to be able to interpret all the numbers or have to memorise the numbers? No and no. You're aware of what you're going to see. And so all you have to do is understand. Answer the question. In the assignment, there'll be, hopefully everyone's mature enough to understand. It's not as if I'm going to ask radically different questions compared to what you're doing in the assignment. There will be question or questions associated with McGowan, Weir and Chen's presentations. They are there they're meant to be the easy mark questions for those who bothered to turn up. If you didn't bother to turn up, it's going to be a bit harder. You'll have to review the presentation recordings. The presenters have confidentiality associated with their presentations, so I can't just give you the PowerPoints in PDF form. The last thing is, it's not as if the questions I ask are going to be radically different in style from what others have been asked. Such and such said something. Such and such asserted something. We're not talking about truths out of the book here, by and large. It's about information that was communicated by the presenters. I recommend everyone who has seen, this is your second subject with me, you've already dealt a lot with factors of safety, all this stuff. Factors of safety is something that you don't just use and forget. You will have to recognise it throughout your professional career. Thus, and this subject, factors of safety, is still important for the designer. There is likely to be a question associated with factor of safety in your exam. And down the bottom left is the important bit of information. I've actually provided the lecture material from the 3rd year subject that has the development of this idea of factor of safety for your reviewing pleasure. Now, this is that bit I said where everyone mumbled and, whoa, what's he talking about? Here was the question that a student asked me, and it was this bit out of the handbook. Students must pass all assignments at the end of semester, and the end of semester exam in order to pass the subject. I wanted to have and achieve a satisfactory standard in the exam to pass the subject, but the system wouldn't let me have those words. Now that's the letter of the land. That is, the handbook is supposed to be like a, written in stone truth. But now let me tell you how I actually, at the start of the semester I don't say anything about this because I want everyone to work hard on the assignments. I want you to engage in the assignments. That's, I can't remember the whole thing, but you look at it and you think, oh yeah, fair enough, forget. You hear it, you might remember it, you do it and you understand it. This is design is about doing, and I hope that at this, week 12, if you don't agree with me, at least you understand that I've been true to what I want from you. Do. Oh, there's not enough tutors to help you, demonstrators to help you. I'll put some more in the room to help you. I want you to do. I want you to learn through doing. So, we're at this end of the semester. Hopefully everyone's at least satisfied, if not happy with your assignment marks. What I do now is I get an Excel spreadsheet with your assignment marks, I add them up, then divide by whatever to get to a mark out of 60. Then we mark your exam, I get your mark for that, and I just add those two numbers together. And the only time I ever think, oh shit, is when, let's say, a student's got 90% for the assignments and 10% for the exam. A real drop-off. That's when I get a bit worried, and that's when I may use this reserve power. If you have worked hard and achieved well in the assignments, I can promise you, you'll do well in the exam. You might not, you might not pass it, but I've just told you the way I do the summations. So, your job is to just, again, like I've always said, work hard, do your best, and that's it. I will then do my half of that contract is that I just add up the marks, and if it all looks like, yeah, good, a bit of a drop off there, obviously a bit stressed in the exam, I get why those mistakes were made, I do nothing more about it. Okay? So that's the contract I have with you. That is not true to, look, it's been recorded, but it's not true to what the handbook's saying, because I'm not happy with how the handbook is written. And I've told you the whole story. Is there a question on that? No? Gotcha? Fantastic. There you go, hints. Any question on the hints? All pretty clear? All right, how are we going? Fair bit of time. This is what you'll see without the questions themselves in 2017. 40 marks for Part A on structural integrity. 4 equally marked questions. For Part B on quality issues, 30 marks, not as much time spent on it. 4 non-equally marked questions. I'll give you another hint on Part B. Part B, apart from that fantastically complex engineering drawing, I assert will be a little bit easier than last year's Part B. So that's something to just acknowledge, to take home with. And Part C is, because everyone got 90, it's just such an excellent outcome for DP1. I did promise you it was the easiest of the assignments, and it was sort of like the shortest topic. There's just a couple of questions at the end, 20 marks for Part C on material selection. So now let's get on to some sample exam solutions. So I'm going to jump ahead. You had a weldment, an I-beam vertically oriented with a couple of plates and a pin. Blah, 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 lots of words. What's the weld height that we've got to specify? First point is that you've got a spot where all the 6 welds are located. And so same kind of stuff that I talked about before. It's essentially a C shape. They sometimes call it a channel. I've talked about, it's a very similar sort of shape to what I spent a fair few minutes talking about in the weld lecture a few weeks ago. You get the idea. Hopefully there's a cantilevered load applied to the pin. It's going to try and twist So it's got a moment applied. It's also got the shear, the direct shear associated with that force. So there's some stuff to be done. It's not totally symmetric in terms of the weldment appearance. It's a C shape. So you've got to locate the centroid or centre of gravity, G, for the weld group. Work out what the associated torque is, which is just force times distance. Don't forget to divide by 2 because there's 2 welds in parallel, so it's 30 kilonewtons each is a reasonable assumption. If I don't say consider factor of safety, fine, but if I already have. Sometimes I'll set up a question where factor of safety is actually the answer we're looking for. Is it safe or is it unsafe? So you've got to find your torsional stress, your direct shear stress, apply an equation of some form or other to get down to throat thickness leading on to the height of the weld, H. So it's just that standard triangle type form. Here's a schematic graphic of the overall process. 30 kilonewton per side. We've got to find our G. Y dash, you could just say by observation, by symmetry. X hat, or X dash, not as easy because of, we don't have a weld red between B and D. What's up on the screen as well as that is just Tor double dash. I've gone through this in class. I'm not going to bore you with it again. But the trick about all this is that we've got this, at certain distances from that centre G, we're going to have different force magnitudes. And everyone in the room can see that the highest forces are right at those edges. So we can be pretty confident even by observation. That's where we're looking. But then we've got to add our, don't forget the primary, that was a funny thing, it went a bit of green, bit of blue. Primary shear in green, secondary shear, the resultants in blue. Don't forget, I've tried to communicate that X and Y is okay for the setting up, but by and large, I'll be looking for you to think in terms of centroids, in terms of resultants, in terms of 2 force members, 3 force members, as per lecture and assignment work. So you can quickly get to this point of saying, okay, we've got a radius there, and we know that that force vector in blue is going to be normal to that radius. That's the kind of insight I hope that everyone in the room will present for me in the exam. Oops, did I go back to? No, that's it. Once you've got worst case force, that can be shoved into the stress versus force equation that might be provided, might not be. You'll certainly be given a maximum stress of some form or other. And once you're there, stress to area or section will be the process to get to an answer. I'm going to jump ahead to show you the object itself. There it is. I'll just give you a big hint here. If I was going to give you a mechanism of this ilk to work on, I would show you the mechanism. I wouldn't give you any hints about what it's for, but I would show you an image of it. Okay? So, but that doesn't mean this idea of something that looks really nice in its pictorial view, its manufacturing drawing view. It looks quite, plausible as a two-dimensional object. But I can promise you that there are a heap of problems with it. Conceptually it's okay, but the constructional, detailed design of it, that is, how it gets put together and how it works, has got lots and lots of flaws. And there's nothing wrong with the material choices either. So the student or the young developing engineer is asked to identify 5 problems. So it's a Revolute connecting rod crank. Okay, so turning revolving energy into prismatic energy. And there's a whole lot of stuff there, and there's some answers in italics. I know people can't read them up the back. This is something for homework. Bang, you've got it. Have a look later. One I will comment on is we've got a bolt. You can't, you've got an object. If you're going to put a bolt, you've got to sort of be able to get to the bolt to tighten it up. There's another one, and that is that this all looks very nice here, where we've got a bolt and we've got this rotating arm, we've got our connecting rod. But as soon as this arm tries to go to about this angle, that point tries to get to there, this bit of material is going to start wanting to interfere with that central axis bit of material. The learning in that is for you, the developing engineer, not just to see a static object or a series of static objects, somehow stuck together, but what does it do? Can you visualise in your mind the movement of that object? So that's if you like, one of the skills that this question is seeking to ask. Question A3. I'm going to jump ahead to the structure. There's this funny structure. We've got 50 units of force applied to this structure. It's the one closest to us. We've got 3 other similar but different structures with forces A, B and C being applied to them. And the question that's asked, back I go, is what are the loads as a, if you like, a ratio compared to 50 that A, B and C would have to be? What magnitude would we have to have A, B and C that would cause collapse of the other 3 structures, just as 50 causes collapse of the first one? It's quite a nice little bit of, if you like, homework question. We've got a certain shape for the first one. They're all pinned at that end, which is trying to communicate to you that the top part can just move freely with respect to how it's all oriented. What happens at the top beyond that is a bit interesting. Pin joint for A, pin joint for C, fixed end for B, fixed end for the first one that's given. We've got to look down the bottom as well to see how the end fixation is for all those. I missed the most important point before I started yapping about all this. It's a column problem. It's, is it a long column, is it a short column, is it Euler or Johnson? And let me just go back. I don't know if I say anywhere in the question that it's a column problem. No. So the first point of recognition for the student is to say, okay, column theory. Let's start applying what we've learnt about columns. And let's just say there's an exam question like this, and in the associated lecture I did talk about the end fixation and the equivalent or effective length of a column. And so depending on whether it's free, pinned or fixed, or rolling element down the bottom there, we can have different effective lengths. Now that we're dealing with sort of closed book exams, you would be given a table in the exam to use. Because in the lecture notes I did talk about how different resources use slightly different numbers. And so for the practitioner engineer, that's something to think about, something to be not concerned about, just to recognise what's the difference between the standards, what's the most recent, is it from a higher authority that sets that standard? But for the here and now, so you don't freak out, you don't ask the wrong kind of question of yourself. In a high pressure, time critical environment, that sort of stuff would be given. Now, without the method, there's the answers. Something for you to work on as study in advance of the exam for me. Okay, question A4. Blah, 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 blah. Question that you've already seen. So place all external and body forces on the whole door stop assembly to show equilibrium as the door is opening. Now, when it was open book exams, I would never ask a question like this. A question like this in the exam, because after all, the whole class has done it. Now on, it's a different deal because, if the whole class has worked on every question, as I would like you to, you're as a team sitting at a table saying, yeah, I don't get that bit, and your teammate helps, or even some other people come and help. You all learn in a team-based environment. And then you go into an exam, something like this would be just, everyone would get it. In an open book exam, the people who, let's just say, slacked off a bit and weren't active, even for this question, would still, if they at least just took a copy, would be able to walk in with a copy of the answer. Thus, there's no demonstration for me of learning in this assessment portion of your experience with me. But that's no longer the case. So questions like this are now valid for me to ask in the exam. I would regard them as the easy questions because everyone who's done it and gone to the follow-up Q&A sessions and the follow-up here's the answers questions and written it down has got it in the forefront of their mind. Thus, it's an easy one. For those who haven't, well, they'll think, shit, I wish I had been a bit more engaged when we were working on that problem. So, similar to what's in the DP assignments. So that's a series of questions of the style that you may likely see in your exam for structural integrity. Now, this is the kind of question for the guest lectures. Briefly summarise Philip's reasons as to why Ford was able to emerge from the global financial crisis in a better financial situation than its competitors. Philip didn't talk about that this year, but I can actually answer that question for you. And Philip said Ford evolved well because they rationalised their factories in advance of the 2008 global financial crisis. A lot of small factories around the world got closed, and the larger factories had greater production rates. It turned smaller cities into ghost towns, but it put Ford in a better position financially when there was a big downward impact, and a lot of people weren't buying cars. He went on to say that General Motors and Chrysler both asked for federal government handouts in the US, but Ford didn't. Ford Australia limped on for a lot longer than it otherwise should have for that very reason. That's why Ford Central was always sort of thinking about closing Australia, because it was one of those little minnows of manufacturing. And it was going against Ford's international philosophy. So I've said more words than you would have had to have said, but closing small factories, getting economies of scale, both would have been correct for that question. So, all you've got to have done, and look, the brightest student would have attended Philip Peters and John's lectures and watched when I went, oh yeah, I'll write that down, because that's when I thought that's a good point that I might be able to use for an exam question. So you weren't, those who were there and saw me do that, well done. For everyone else, that's how to succeed in what is supposed to be pretty easy questions. I did talk about in the tolerancing stuff that there's thousands and thousands of different permutations and combinations for limits and fits. And so pretty much every year, I think in the previous exams, there's a question of this ilk. Sometimes I ask for scaled deviation diagrams, sometimes not. Thus, that graph paper I showed earlier might be to help you with your scaled deviation diagrams. Type of fit's got to be, if you just, look, the student that just says, oh, table, number, boxes, numbers on edge of the boxes, finished, move on, half marks, you've got to actually say, you've got to sort of demonstrate you understand what it is and why you've done it. And one of the ways of understanding is, what type of fit is it? Clearance, transition, or interference. And this idea of expected fit, the mean and variation, further indicates that you understand why the hell you've even bothered to get those little boxes of tolerance produced. So I'm pretty confident, that this is a scaled deviation diagram for question 1. And I'm not giving you all the process, I'm just giving you the answer. You can go through the process, check my answer yourself. Hopefully I've written somewhere, there we go, in red, a clearance fit. And sorry, this deviation diagram is only partially scaled. Those two, that's good I've done this and told you about it. The boxes are scaled within themselves. But these clearance arrows, or distances, have got those little dashy lines across them to indicate, to do it in a fully scaled way sort of loses the opportunity to be able to put the tolerance diagram into a reasonable state. That would be perfectly acceptable if I saw you do that. You demonstrate you understand what you're doing. And the expected clearance goes through all this blah, blah, blah. We've got it to there. You can leave it at that point. That would be adequate for me. The student who chooses to actually go a bit further, develop those numbers out. 189.5 plus 20.7, 189.5 minus 20.7, explicitly stated. If you want to, if you've got time, I don't mind. For the second one, a bit harder, we've got a transition fit. We've got an interference maximum and a clearance maximum. If in this case you had two I's, two interferences, one of them would be negative. If you had two clearances, one of them would be negative. And people who were in the room at the time, I said that this whole, we can't have negative space. We don't go into sort of the negative realm when we're talking about the physical world. So you see a negative number, you think, okay, clearance has moved into interference. The easiest way to think about it is to do the diagram. And you just think least to most to least. And for the majority, to be blunt, who weren't in the room when I was getting all excited about this stuff, go back to the lecture recording and review that material, and you'll get it. Question B3. I'm going to go to the plate. Again, given that everyone, or pretty much everyone's here right now, there will be benefit, I think, in going back and looking at the lectures on all this stuff, and you'll pick up pretty quickly. There was a tutorial that I went through in great detail, and there was a lecture on this stuff with some examples, and we're not going deep in this realm. A plate with a hole in the middle, pretty simple stuff, but it can get pretty complex pretty quickly. We're after a gauge from memory. There's datums, primary datum, secondary datums, tertiary datums. Talked about that, fully worked example. Complete an isometric sketch, identify the datums, and then complete an orthogonal sketch of a gauge to achieve it. So there's the object. There's some of the stuff listed on that object in terms of all the tolerances that I've talked about at great length. Sketch. It's all we're after. Flatness, A. Perpendicularity, B. Perpendicularity, C. Size and location of pin for the hole, so that we have a degree of confidence that the plate with a hole meets the sort specification. And beyond that, there's a heap of stuff excuse me, associated with what's important as we're considering the values associated with tolerancing that part, that object, and how the gauge is going to accommodate it. Part C. Looks like I'm going to do it in time. I have warned the class that I like asking questions like this, and this is a pretty easy one. I just come up with some goofy ratio of performance indice, and it's your job to linearise that equation and work out what the power is. Excuse me. The resultant power has everything to do with slope on the material selection chart. And when I set a value for m, well, that gives you the starting point to locate a line on the chart. I think there was an assignment question on it, but I can promise you that the material notes, the lecture notes I've given, hopefully have got to the point where everyone should get good marks for this. And here's another hint. In my opinion, answer part C first, because it should be the easy mark earners. Then move back through the rest of the paper looking for a friend calls it the low-hanging fruit. The questions that you think, yep, I can get that done fast, get that done fast, get that done fast. Get the easy marks out of the way first. So there's a bit of the answer. linearise into log form, rearrange, and you'll find that the gradient on a log-log chart is 3 on 2. Just hopefully, you know, I don't go, I can promise you, I won't tell you E equals Young's modulus, rho equals density. I'll presume that to be learnt, you know, well, just so ingrained in your thinking now that it's there, easily done. So that you can readily then choose which of the charts you have to use. I've mentioned that because sometimes students under stress of the exam get the wrong, they just go to the wrong chart. I'm thinking, you know, all your symbols are right in the development, and you just sort of jump to just any old chart because you're not concentrating. I hope no one in the room does that this year. Excuse me. The thing down the bottom is what I've said in the past. Different people will have different approaches, but there is no zero intercept in the y equals ax plus c form when we're dealing with log-log equations. So, my approach, boonk, is to choose, you know, density equals 0.3, put it into the equation, and make sure I can work out what, well, let's go with 1. Density equals 1. What's the corresponding Young's modulus? Blue dot gives us that point. 3, 10. So I've got 3 points. If all 3 points, I can put a line through them, I can be comfortable that I haven't made an arithmetic error. Exam preparation technique. Make sure that you can play it with the units. It all works out for you. That you can, you know, I can promise you that, I can tell you, I've got an Excel spreadsheet where I play around with this stuff to make sure that that whatever the line is, wherever it is, it's going to be within the chart. Thus, I've gone through the process of making sure that I've got consistency of units to get the answer I need. Now, there's been questions, I've had tutorial questions where all of you have the same opportunity to get the same learning. Good exam preparation. And I can promise you that if you do what I've just said, try and get those blue dots, and they're not on the chart, I can promise you that you've made a mistake, because I've done this so many times. And beyond that, the important thing to note is the questions C1b and C1c explicitly identifying the part of the question that you are answering for me. And then question C2. We've got a tie of length L loaded by a tensile force F. Now, sometimes I might just, you know, a tie, without that pretty picture down the bottom, only the people that have bothered to study and remember that a tie corresponds to an object that's under axial tension would be able to move beyond that first 2 words, a tie of, because, you know, others might just think, oh, like a bow tie, or, you know, something that you wear around your neck. This is the lexicon of engineering that sometimes, it depends on how I'm feeling, really. When I first asked this question many years ago, I didn't actually have the image in there. You know, I harped on the idea that a chain, a rope, a tie, a link, dot, 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 all words for, you know, a component under axial tension, and then set the exam. Now that it's going to be closed book, it'll be less likely I'll do it that way because, again, under stress, people might have forgotten, there'll be an image like that, bottom right-hand corner, so that everyone's got the same opportunity to move into the question and not be limited by language, not be limited by, you know, technical words. So there's a few questions associated with it. A, derive an appropriate performance index indicating the objective function and equation, constraint equation. Pretty easy question. Follow the approach used in lectures. Easy mark type question. B, draw an appropriate material selection guideline for the tie. Strength versus density. And it's down there, I'll just flick it up there. The tie is one of the 3 standard lines. You know, I could have said a beam, I could have said a plate in bending. They are like, oh, means it's beginning it as an easy question. Don't have to find the gradient. it's been given. So I'm going to go back a couple of slides. Boom. Got the guideline. And I'll just go forward. All you had to do was just highlight it. Don't have to put it anywhere in the middle, just to say on the chart, it's given, thanks for the easy marks. Then C, indicate the optimal material selection for this design scenario. The student that wasn't in this room that said diamond or silicon carbide, that's for material selection in compression. They're good in compression. Tie is always in tension, sorry. So best response was that, yielding, metals and polymers, whole heap of stuff therein. That would be the kind of way of answering the questions. So wrong up in this zone with that dashy line, because by that particular information box, which I've talked about. And we're just moving that orange line in parallel all the way up there, finding, we can't necessarily choose those. Beryllium is up there. It's not dotty, but let's come back and be safe. Or I might make it more explicit and say, of the engineering alloys, which is the best? That sort of thing. That's the sort of shorthand. This is a question associated with size factor, or shape factor, sorry. We've got our standard performance index, we've got a shape factor, and then there's some questions to be asked. And I'm just about out of time, so I'll zip through to the answers. I'll just get over there. Which materials with the shape factor equals 1 have compatible performance with the earlier material? Then B, show that the mass of a stiffness limited tensile element is independent of shape factor. So there's a bit of answer for find zinc, because that's our starting point. We've got a certain type of shape factor, and hopefully everyone will remember that material woods tend to have that, we can't have long and thin, we can't have thin walls, etc., etc. So if we're going to, and I've talked about aluminium compared to wood in that regard. So zinc with a shape factor to 10, there's an expectation that that kind of thinness would allow us to have performance, equivalent performance in things like bending to these kinds of woods with just solid circle, solid square. That would be what's required. And it's just a replication of the type of stuff I've talked about in class. The first part of the question was just to indicate, we're looking at a tie type object yet again. Almost done. And for this question B, simple. There it is there, answered. So have a look at that. And we're done with 1 minute to spare if you have a question. Yes?
Just with that column question before.
Yep.
Are we required to know all the second moment per area?
The question was, is the student required to know the second moment of area of column shapes?
Yeah.
I'm not a big fan of memory, and so I would hope that everyone remembers BD cubed on 12,
Yeah.
but pi r to the power 4th on 64, a bit harder, so it'd be more likely that it'd be given somewhere without context. Okay? Any other questions? Now, I know people are packing up for the next thing, but this is the time. Sending me an email in 5 minutes is not the time. If you're all comfortable and relaxed with what I've said. Okay, well, thanks very much for your time. I look forward to seeing you next semester, if not before. Oh, thank you. Thanks very much. Oh. Thank you.
You wanted to take over? Hey? You wanted to take over or? No, just wanted to. We'll have to wait for a moment.
Okay. That's cool.
I'm doing master of electronics. Design is not important to me.
Okay.
But I want to do design for integration.
So you open this semester.
I was thinking of overloading and doing 5 subjects. I have the option of doing it assessed and non-assessed.
Okay.
If I do non-assessed, does that mean I can't take part in the group project?
I don't know. You have to ask someone about that.
Because the reason I wanted to design for integration is so that
Should be part of the group. So I get it. That's what it's all for. So look, I'm as long as you're motivated and you want to actively participate in a team, I'm supportive. But you have to ask stop one about that. No, it's not okay because I don't know. I really don't. Because if it's not assessed, do you get access to LMS? I don't know. So those sorts of questions you have to ask someone who knows more about it than I do. That's all right. And hopefully you enjoyed this subject.
Oh yes, I have. You're the best lecturer I've had.
Oh, you can say that because I'm here.
No, you actually, most of the lectures are here for the research and referees and obligation.
Yes.
But you actually really want to teach.
Yes.
It's a better experience for everyone.
I appreciate that. Well, thank you. I know you've been in the classroom too, so thank you for coming along.
Thank you. I'm
Done.
definitely trying to get into DFI.
Oh, great. Hopefully to see you then. Bye. Nice. And you.
I guess the seats are different color. Why are you gonna have this? Do you want a hat?
No, because the hat color clashes with this color.
It doesn't clash and match.
Hello. Oh.